proportions was part of homework 3-1. I want to make sure that you guys are understanding how to do proportions because we've got not only a direct proportion, we've got inverse proportions, and now we've got squared proportions. I don't have my pointer, but we have the velocity squared, which means that we've got a proportion that increases by a factor squared. So you want to be able to understand proportions for the test, which is on the 15th. This is a really short unit. And if you struggled on homework 3-1, you want to make sure to study that. So for the first one, we are trying to find the relationship between period and speed. The equation that has period and speed in it is the 2 pi r over t. In your seat, please. And because the radius is in the numerator, if my radius increases, my velocity increases. But if I'm looking at the period, notice the period is in the denominator. We know that if the denominator increases, the velocity decreases. And so in this scenario, they did a proportion. They actually plugged in 1/2 t. And then they got a value of 4 pi r. It might seem like it increases by 4 times, but remember, our equation has 2 pi r in it. So what you want to do, I want to make sure that you still include the t in your equation, but what you want to do is to show how this compares to the original, and compared to the original, the speed actually doubles. Does that make sense? Any questions? A decrease in period increases the velocity, and an increase in period decreases the velocity. They're opposites. Any questions on one? For number 2, this group is trying to find the relationship between speed and acceleration. So they actually, what did they do? They used number values. Did you just plug in number values into the scenario to get a relationship? And I had a group in my other period that did the exact same thing. Some of you like learning with concrete numbers rather than variables, and so plugging in values is perfectly acceptable. So in this scenario, they took a velocity and a radius of 1, and they calculated it out. In the second scenario, they quadrupled the velocity. Was it the velocity? By a factor of 4, and then they simplified it out. Their answer was a factor of 4. They did the work correct, but there was one step that they were missing. Mur.
Before the all the
So be careful, because if you're quadrupling the velocity, the 4 is part of the velocity, and you want to make sure to square that 4 also. If I squared the 4, I would end up with 16, and when I get 16 here, it actually increases by a factor of 16. This is my square proportion, okay? As the velocity increases, the acceleration increases by a factor squared. The graph looks like this. For this one, we've got an inverse proportion, and that proportion looks like this, a decrease. Last but not least, we've got the force related to the radius. And as I stated before, the force equation doesn't have radius in it, but the acceleration equation does. So we're going to combine the two and use this one. The radius and the force, notice the radius is in the denominator. They're inverse proportions. So I did this wrong. As radius increases, force decreases. And so in this scenario, they did the same as group number 2. They plugged in values. They took 1 as their original and then doubled it in their second scenario. And then they showed that the relationship between 1 to double is decreased by a half. So I actually like the different methods that I'm seeing up here. Instead of thinking about relationships, you can also think about the plugging in values and looking at numbers. This again is an inverse proportion. As one increases, the other decreases. So the graph would look like this. Any questions on proportions? I'm going over it now because it is going to be part of your test on the 15th coming up. Okay, let's move on to one presentation. It's a short 2-minute video that I want to show you because it's Native American Heritage Month. And I always want to take some time to recognize some important scientists in that field. So how many of you seen Hidden Figures? Hidden Figures is a really, really awesome movie about the amazing women that were part of NASA's program that never got recognized. And so one of those women were Mary Ross, and I want to share this presentation about Mary Ross. Okay, so let's talk about planetary motion. For Kepler's first law, you should have noticed a pattern. When I click all of these boxes, and this is my Earth, right? It looks pretty circular, but look at my R1 and R2. Let me slow this down a little bit because it's going really fast. My R1 and R2 are spaced out when it reaches the top. So you can see that it's not a perfect circle, although most planets do revolve around the sun in nearly circular motion. What's the planet that does not revolve around the sun in circular motion? You had it as part of your question. Ethan. Pluto. We call it the dwarf planet because it is actually more elliptical. So planets actually revolve in elliptical motion, even though they look pretty circular. It's just a really low eccentricity. And the way your first analysis worked was regardless of, let me get a bigger ellipse here, regardless of R1 and R2, no matter where it is in its motion, R1 and R2 added together would make the exact same total. So it doesn't change if I'm on the very left or the very right. It's always going to stay, in this case, 2 AU. So a better visual is to actually use a string to create an ellipse. This is what we do when we're in art class. I think my daughter did it in 2nd grade. You have 2 centers. We call it the foci in an ellipse. And when you have 2 different centers and 1 string, this string is not going to change length, hopefully, because in my last class it came out. But if I keep the string the same length as I go all around the ellipse, and I'm going to try to do this nice because I tend to go too fast. If I go all the way around my ellipse, I end up with a pretty long elliptical motion. The sun or whatever planet your objects are revolving around is always going to be at one focus. And your planet is going to revolve around the ellipse. So Newton's law number 1 is that planets revolve around their sun or their star in elliptical motion, with the sun at one of the foci. So I have a slideshow. Each planet moves in an elliptical orbit with its star at one focus. If you wrote something down, make sure that it matches this description because it is going to be included in your test. All right. Ready for number 2? When we did Kepler's law number 2, we had things called sweeps. And the sweeps looked triangular. And let me just pause my animation. If I moved this triangle from one side to the next, you're going to see the closer the orbital path is to the sun, the wider that sweep gets. And what you should have also noticed as I start my animation is where does the planet go the fastest? Let me speed this up because you can see it a lot better when it's faster. Where does the planet move its fastest? Closest to the sun. So the idea behind the sweeps, and Kepler noticed this pattern, is that the amount of time it takes for the planet to cover this section is the same as the amount of time it takes for the planet to cover this section, which is representative of how slow the path is when it's far from the sun and how fast it is when it's close to the sun. So here is second law, which states that an orbiting object will take the same amount of time to travel between these points and these points. And you can draw the diagram to help you, but basically the result is that planets move fastest closest to the sun. That's the end result of Kepler's calculations, which is Kepler's third law. Anyone still need the slide up? Okay, I'll put it back up if you need it. But Kepler's third law was showing the fact that, let me just pause this because it's distracting. The fact that your period and your acceleration have a relationship. And this 2 right here was in the wrong spot. It should be 1.88 squared and 1.52 cubed. But the A represents the axis, the semi-major axis, and the P represents your period, the amount of time it takes to revolve. Kepler noticed that if you square the period, it equals the same amount as if you square your average radius. And so this is your last law, which shows that the square of a planet's orbital time, your period, is proportional to the average distance from the sun. So P squared is proportional to R cubed. Now recognize, even though planets move in nearly circular motion, they use average radius because it is actually an ellipse, and the radius changes depending on where that planet is just by a small amount. So they take the average radius. So period squared is proportional to radius cubed. I want you to pull out this worksheet. You weren't supposed to do this. We're going to do this in class, and you guys are going to finish the details at home. Question? No? But is this, you were absent? Okay. So let's start with, I actually need you to grab maybe 2 or 3 colored pencils. If you have highlighters or colored pens, that works as well. But if you need colored pencils, I'm gonna need my own.
You see? Yes. You get it. I didn't have it.
All right, be kind with my materials, please. All right. Carson, put that away, please. I don't want to see it out again, or it's mine.
Do it again.
Everyone in their seats. I do want to make sure we have enough time to cover all of this. Lincoln, Joey, set. Or can I have you face forward, please? I want to see eyeballs. Eyeballs in my direction. Okay. So, first of all, you learned about, you did your reading, and they talked about objects that are revolving around a planet. And we're going to talk about what's called satellite motion. And satellite motion is circular. So the way it works is that you know that when you launch an object horizontally, it moves in projectile motion. Even though it's moving to the right, what forces are acting on it? If it's moving, in this scenario, moving to the left, what are my forces if I were to draw a force body diagram? Who can tell me? What is acting on this cannonball? What is acting on all objects on Earth?
Gravity.
Thank you. Is there any force pushing it to the right once it is launched? Or sorry, to the left?
Yeah. No.
After the cannonball has released it, there are no leftward forces. This is what we call free fall. And then if I were to launch it a little bit faster, this is B, it's going to land right here. So this is path B. You're drawing this on your paper. I'm giving you the answers, so follow along. All right. Newton came up with this speed, 8 kilometers per second. And he said that that was the speed you needed to launch a cannonball from a certain height to get it in what they call satellite motion. So they launch their cannonball in the same way they do, but this time when the cannonball falls, it misses the Earth. But it still has gravity pulling it toward the center of the Earth. So as it moves, it creates this beautiful circular motion. So for C, what would the path create? Or sorry, for part B, what is the shape of the curve in this scenario?
Ellipse.
Is it an ellipse yet? It's a circle. But you kind of led into our next topic. What if I shot it just a little bit faster than 8 kilometers per second? You would get an ellipse. So it's hard to draw the ellipse just because this is so narrow, but your ellipse would come out, in, and then just kind of like an egg shape. Kind of like that. That would be your E scenario. Elliptical motion. I'm going to kind of go through this quickly, and you can fill in the tiny details after I've gone over the most important concepts. But let's talk about figure B. This is satellite motion. The satellite has been launched already, and it is moving in circular motion around the planet. And what we know about circular motion is the gravitational force is the only force acting upon it. If I were at this position here, what direction would my gravitational force be pulling? Can anyone tell me? Mert? It would be pointing to the left. Or is that the left? To the, your left, my right. So this is my force of Earth. If I had it up here, what direction would it be pointing? Ayush? Where? Down. Good. All right, draw the rest of your forces for each of the different positions. You guys get the idea, right? Hopefully. Okay, so we're going to jump to part C because part C is related to the force of Earth. Once you've drawn all your forces, what do you think about the length of those forces? Do you think those forces are going to have the same length?
Yeah. Yeah.
Why? Grace? It's circular, which means that the radius stays the same and it's equal on all sides. So it's the same because it's same length because distance from the planet is equal throughout its entire motion. All right, next one. I'm not going to draw the rest of the forces, but I want you to make sure. What direction should all those forces be pointing in? For those of you who drew it, into the center of the circle. So for all of these, they should all be pointing inward. Now let's talk about the tangent velocity. We talked about tangent velocity in circular motion. We talked about it in Kepler's law. The tangent velocity is in the direction of the motion itself. And since it's going counterclockwise, it's going to be pointing in that general direction as it's pointing around. But tangent velocity means that it only touches the circle at that one point and moves straight out as if it was perpendicular to the circle right at that peak. So this is my velocity vector. What direction would my velocity vector be pointing if I was right here? Who can tell me if it's moving counterclockwise? Aish?
Wait, if you're at the top?
If I was right here, what direction would it be pointing? It would be pointing down. Tangent velocity would be pointing down. All right, so I want you to finish off the rest of your velocity vectors. You have your force vectors, you have your velocity vectors. And just like we did with the force, do you think the velocity would be the same length? Do you think the speed would be equal all the way around? What do you guys think? Do you think it's going to have an area where it's faster? Think about Kepler's law. Any thoughts? Come on, people. Is it going to speed up at any point? Rua? Do you think it's going to have the same speed or changing speed?
Same.
It's going to be the same. So what I want you to do, so hopefully this is what your force body diagrams look like. I want you to draw symmetry lines. Your force of Earth should have equal force. And your velocity, even though my velocity vectors don't look equal, this is how it should be directed, should have equal force. And I use double symmetry lines for velocity because velocity is not necessarily equal to force, but they're all equal to the velocity vectors. And the reasoning is the same. This is due to Kepler's second law and the fact that the radius or the distance is always equal. Can anyone tell me the angle between the force vector and the velocity vector when I have circular motion? What angle does that create for those of you who are in geometry or trig? But it should be common sense. 90-degree angle, right? These are all perfectly perpendicular. That's actually jumping to the back page. So I want you to flip it over. We're going to write 90 degrees. And then I'm highlighting important parts here. You can underline it if you don't have a highlighter. But I want to highlight that a net force acting perpendicular to the object's motion will change its direction. And I'm adding this here, not its speed. Speed does not include direction, so its speed stays the same, but the direction is changing. Okay, let's move on to this part where we now have elliptical motion. This is how planets will move around a sun. And if you shoot your satellite fast enough, you can get your satellite in elliptical motion also. So what position do you think the gravitational force is the greatest? And then what position? I want you guys to actually work together to answer A, B, C, and D. Just think about where the force would be greatest and weakest and where the velocity would be greatest and weakest in the scenario of elliptical motion. Not circular, but elliptical. I'll give you 2 minutes to collaborate with your partners.
It's not late.
I do want to. Joey, this is late. Is this late?
No.
Where you didn't? Did you have it complete at the beginning? Oh no, you have your stamp. Sorry.
See?
I am going to call on groups to present their answers, so make sure you're all in agreement. I see mainly students working by themselves.
I'm really far away. But like the arrows, this arrow. Alright, you guys do it. Maybe it's like more
All right, so let's start with the first one. Let me have someone from group 5 in the back there. What do you think is going to have the greatest gravitational force? What position? C. How do you know? It's closest to the sun. So here is the thing about gravity. The closer you are to Earth, the more you feel that negative 9.8 acceleration. The further away you are, the less you feel that pull downward. And then once you're way out in outer space, you barely feel it. It's still there, but you barely feel it, and you don't have that pull toward the center of the Earth. So gravitational forces are always existent, but the further you are, the less you experience it. And it's the same relationship we have in this equation. F equals mv squared over r. R is in the denominator, so as r increases, force decreases. In this scenario, C is going to have the greatest force, so I'm going to draw a really long force arrow. All right. Where am I going to have the weakest force? Andrew?
A.
At A, because it's the furthest away. So same reasoning. I'm going to draw a small force of Earth at A. Okay, let's talk about velocity. And in this scenario, we're going clockwise this time. So we're turning over to the right. I'm going to use a different marker, a different color to represent velocity. But where's my velocity the greatest in this scenario? Any volunteers? Kaylin? B?
B.
Joey? At C. So why do you think so? I still need a reasoning, and I'm going this way because remember it's moving clockwise. Why is it the greatest? Any help, Sammy?
Because it's closest to the sun.
It's closest to the sun, but also it's because of Kepler's law. Kepler's second law, which states the closer you are to the sun, the faster your speed. Okay, so now that we know that, what's going to be my shortest velocity, my slowest velocity? Roberto? At A. So I'm going to draw a short velocity arrow at A. Okay, these are perpendicular also. And what did we say about perpendicular? It changes its direction, but not its speed. Okay, let's go to B and D, because B and D are going to give us different types of vectors. First of all, in an ellipse, we don't think about the center the way we do the center of a circle. So the center is not here. And our focus is actually some invisible empty space here at the top, and then the sun. So if we were to draw a force for D, what direction do you think I should draw that force vector in if I was satellite D in this position? Any thoughts? Toward the sun. So it's actually going to be angled. But between D and B, which one should be larger? My force. D, because it's closer, right? So I'm going to draw D a little bit longer than the force, a little bit shorter than the force of Earth on C. And then this one is going to be even shorter than that, but they're both pointing toward the sun. So notice how I have my largest force, medium, a little bit smaller, and my smallest force here. My velocity vectors are going to go tangent to the ellipse, and I'm going to have that same relationship here. Smallest velocity, a little bit bigger. This one is going to go upward because it's always it's clockwise in this scenario. So it's tangent to the ellipse. And then this one is my longest. So you want to show that gradual increase in velocity fastest as it approaches the sun. Okay, what we're going to do now is we're going to draw components. And this is something you do when you get an AP Physics and you work with angles. This is the first time we're working with angles. Forces, when they pull at an angle, they have a horizontal component. So this force is pulling to the right a little bit, and it's pulling down a little bit. So these are my components for the force at D. For B, it's pointing to the left, so it's pulling my satellite to the left a little bit and down. Components you want to draw in different colors. Okay. The reason why I highlighted this, let me grab a different color, is because forces acting in the same direction of motion will increase speed. Forces acting opposite the direction of motion will slow it down. Now that we see this position and this position, my velocity is going downward, and here my velocity is going upward. Who can tell me what position will increase the speed of the satellite? Will it be B increasing speed or D increasing speed? Any thoughts? I'm answering part I right now. I can't fit it in my screen, but part I. Which one between B and D would be increasing speed? Sammy. B. Why? My velocity is coming downward. My force is also pulling it downward, right? They're relatively in the same direction. So here we're speeding up. Where would I be slowing down then?
D.
At D. My velocity wants to go upward, but my force of Earth or my force of the satellite or of the planet is pulling it in the opposite direction. So these opposing motions or motion and force would be a slowdown. So that answers part J. And it also brings it back to the fact that when you're moving closer to the sun, you start slow and speed up. Once you move up away from the sun, you're slowing down because your motion wants to move upward, but the force of the sun or the earth is pulling it downward. Any questions on this worksheet? We went over the basic details, but explaining the reasoning why, I want you to fill that out at home, and then I will give you a stamp next class. The next thing I want you to do is flip this over, because I'm going to give you some instructions on how to do worksheet 2 well, because you're going to have a quiz on worksheet 2 next class. I am going to make sure that I have a good warm-up for you to prep you for this. But first thing I want you to do is underline all the given values. So follow along with me. I'm launching a satellite. The launch satellite is Terra, and it is a mass of 5,190 kilograms. You want to do the guess method for this. Terra is revolving around the Earth, and the radius of the Earth is 6.38 times 10 to the third kilometers. The acceleration is the same as gravity on Earth. So A is equal to negative 9.8 meters per second squared. And the orbital altitude is 705 kilometers. So there's a lot of information given here. It's hard for you to understand exactly what it's asking you unless you draw the scenario. So in this scenario, I've got Earth. I have a radius of Earth that is 6.38 times 10 to the third kilometers. Or sorry, km, not kg. And then I have a satellite. This is my satellite. That is a distance of 5 kilometers above the Earth. Abba. Zoom in. My writing is a little messy, but this should say kilometers. km. And this is 705. Okay, so then, first of all, do we work with kilometers in physics? Do we work with kilometers? We work with kilograms, but we don't work with kilometers. How will I convert kilometers to meters? What do I have to do? Multiply by 1,000. We want to get this in meters. Same with this one. Also, I want to use my radius. My radius would be what? What do I have to do to get a full radius? Any thoughts? Sebastian? Put it away, please. What do I do to get my radius? I've got a radius of the Earth. Is that my radius? I've got the distance from Earth to the satellite. Is that my radius? What's my radius? Any thoughts? You add them together. You need to add these two together to get the total distance from the center of the Earth. That's going to be your radius. The next thing you want to do is convert that radius into meters, so multiply it by 1,000. The rest of this, you should be able to figure out on your own. If I have a satellite moving in outer space, think about what forces are acting on it. Are there any contact forces on the satellite? Is there anything touching the satellite when it's in outer space? No. So think about that when you're drawing your force body diagram. Then think about what force is acting on it if there are no contact forces. And the rest of these equations are the same equations you've been using for circular motion. In the back, this is a satellite revolving around Earth. This is Earth revolving around the sun. So they give you more information. Again, this needs to be converted to meters, but it doesn't tell you one important fact, the period. And this is only for problem number 2. Don't use this period for the satellite because this is the Earth revolving around the sun. What is the period for the Earth's revolution around the sun? It doesn't tell me in my worksheet, but this is something that you should know. What is it? What? 1 year, which is 365 days, which is how many seconds? I don't know. Google it. You guys know how to Google. You want the time, which is 1 year in seconds. Once you have that, the rest of the information you should be able to calculate. Make sure you know how to work with exponents in this unit. You want to make sure to bring your own calculator so that you know how to use exponents on your calculator because every calculator is different. We still have 10 minutes. I want you to work through this with your group. I'll come around and check your answers. And also, we are having a quiz on this next class, so make sure you check the answer key video when you finish this at home.